first principle theory of quantum reactive scattering has achieved tremendous success in predicting and explaining quantum effects in triatomic systems. This field has now advanced to polyatomic reactions, and 4-atom and 6-atom reactions have been frequently studied. Here I will discuss two such examples, the OH plus H2 and H plus CD4 reactions. High-dimensional study of quantum dynamics is expensive because of the exponential scaling of the computational costs with respect to dimensionality. Non-adiabatic quantum dynamics is even more complicated due to the involvement of multiple electronic states. Despite these challenges, such a study will provide a much wider spectrum of interesting quantum phenomena.
The study of non-adiabatic quenching of electronically excited OH by collision with H2 has fundamental importance, and it has attracted wide interest among experimentalists and theoreticians for more than 2 decades. There are 3 involved channels: the reactive quenching, the non-reactive quenching, and the elastic scattering channels. The outcome of the collision is determined by the anisotropy of the potential energy surface as shown by this plot. Let's look at several 1D cuts of the adiabatic surfaces. As we know, non-adiabatic transitions often occur through conical intersections, where multiple surfaces are strongly coupled. For this reaction, there are several conical intersections: the linear-shaped C infinity VCI and the T-shaped C2VCIs. The reaction starts asymptotically on this red 3,2A surface. No barrier exists for the excess of the CIs. Here is an animated view of the 3 surfaces generated as 2D cuts in the R-seed H2 and R-seed OH planes. The black thick line in the left panel indicates a CIC that connects the C infinity V CI and the C2V CIs. The linear CI is much lower in energy than the C2V CIs, which will explain the pure contribution of the linear CI to the non-adiabatic transitions. Here, basically we want to answer 2 questions. The first, what's the fate of the OH and H2 after collision? And the second, as described in the last slide, there's multiple CIs, but which one is responsible for the non-adiabatic transitions? Here on the left, the animated wave function on the excited 3,2A surface is shown along the OH and H2 rotational angles. The OH and H2 were prepared in the ground rho vibrational states, so initially OH and H2 have equal probability in all orientations. When they approach each other, the anisotropy of the interaction steers them to 3 regions. The van der Waals region, which does not have couplings to the lower surface, and the wave function in this region will end up into the elastic channel. The 2 linear CI region, where non-adiabatic transition bring wave function to the lower surfaces, as shown in the figure on the right. And interestingly, there's no adiabatic transition near the T-shaped C2VCI. Here's a movie for the overall collision event. The 3 lower panels are similar to the one we have discussed, and the 3 upper panels are the wave function along the distance between OH and H2 and the HH bond length of H2. Large HH bond length indicates the breaking of the H2 bond, and thus leads to the H plus water reactive channel. Here the time starts at 2000 atomic units. Initially, the wave function is on the 3,2A surface as shown in the 2 rightmost panels. Especially in panel C, we can see the initial wave packet enters from the bottom right corner, and when it reaches the linear CI, wave functions start to appear on the 2 lower surfaces after non-adiabatic transitions. On the 1,2A surface, the wave function goes to both the reactive and the non-reactive quenching channels. On the 2,2A surface, the wave function only goes to the non-reactive quenching channel. There are also wave functions reflected by the van der Waals wheel back into the entrance channel. By analyzing the reaction, the wave function, we have calculated the branching fraction for the 3-channel and the quantum state resolved information for the non-reactive quenching channel. To summarize, the calculated OH state distribution have good agreement with experiment. Most importantly, the uncovering of the major inelastic scattering channel resolves a long-standing disagreement between experiment and the theory regarding the branching ratio of the reactive and the non-reactive quenching channels. Here is a study of a 6-atom reaction, the H plus CD4 reaction. The CD4 reactant is prepared in the ground low vibrational state. The products of this abstraction channel are HD and CD3. Both products are formed in different low vibrational states, and we can detect either the HD or the CD3 products. The figure on the left shows the angular distribution of the CD3 products at 4 collision energies. The calculated results agree with experiment pretty well, and the figure on the right is the calculated differential cross-section at a collision energy of 0.72 eV. It displays the velocity and angular distribution of the HD product. Each arc in this distribution corresponds to a certain quantum number for the HD and the CD3 products. And due to the large density of states, the product states are too crowded to be distinguished in the overall differential cross-section. Fortunately, thanks to state selection, a specific low vibrational state of the HD product can be detected separately. In this way, the individual quantum state of the CD3 coproduct can be resolved, as shown in this lower figure. By sequentially detecting all the HD states, the whole differential cross-section can be measured. The results at a collision energy of 0.72 eV are summarized in this box. With all the state-specific information, the correlation between the HD and the CD3 product states can be studied. That is the J1V2 correlation, the J1J2 correlation. Interestingly, product state correlation is only visible in the angular distribution of the differential cross-section. Such correlation entails intricate interaction of the two products during their separation. And the minor correlation here is rationalized by the large kinetic energy release in the reaction. Last but not least, I would like to thank all the indispensable supports from Uwe Mentor, Hua Guo, and Minghui Yang, and also the funding support. Thanks.